Hello everyone, in this video we are going to derive a relation for one dimension steady state heat conduction through slab or plane wall. As we all know that a three-dimension Cartesian coordinate heat conduction equation is given by K in bracket del square T by dabba x square plus dabba square T by dabba y square plus dabba square T by dabba z square plus Q bar equal to rho Cp dabba T by dabba T. Now taking K to this side, so dividing throughout by K, what we have, this K will get cancelled, so it will be 1. The bracket will remain as it is, while Q bar will be divided by K and rho Cp divided by K, and dabba T by dabba T will remain same. Dabba capital T represents temperature, small t represents a time. Now here we are going to assume three conditions. First condition, we are going to have steady state condition. So steady state condition means what? Dabba T by dabba T is equal to 0. The second condition will be unidirectional heat flow condition. Unidirectional heat flow condition means what? Y direction and Z direction is equal to 0. Okay? So we are going to consider only X direction, where y direction and z direction is equal to 0 means what? A unidirectional condition. And the third is no heat generation. So Q bar will be equal to 0. The amount of the heat generated per unit volume will be equal to 0. So this equation is going to be reduced to dabba square T by dabba x square plus 0 equal to 0. Now here, as we are going to assume it by unidirectional, as unidirectional heat flow is been assumed, what will happen? Instead of dabba T by dabba x square, we will write d square T by dx square is equal to 0. Okay? As it is a unidirectional, and so it is an exact differential equation. Further, we are going to integrate this thing, integrate with respect to x. So how many times I need to integrate? I need to integrate 2 times, as we are going to have, I'm here having a second order differential equation. So dabba square T by dabba x square equal to 0, I will mark it as equation number 1. So integrating first time, we have dt by dx is equal to C1, where C1 is constant, Again integrating, here I will mark this as a second equation. Again integrating with respect to x, we have t equal to C1x plus C2. So I will mark this as your third equation. So if I integrate dt by dx, so I will get t. If I integrate C1 with respect to x, so I will get C1x plus C2. So I have marked this as a third equation. So if you carefully see, dt by dx is nothing but a slope, while the equation number 3 will give you temperature profile, because it is in terms of a T, that is capital T, which is nothing but your temperature. Now we are going to find out the value of C1 and C2 from a boundary conditions. Now for the boundary conditions, let us assume a slab having a thickness of B. Say this inner surface temperature is T1, outer surface temperature is T2, and K be the thermal conductivity of a slab. So this is, I have considered this as a slab. So my boundary conditions will be, boundary conditions are, first boundary condition, at x equal to 0, that means I'm considering this to be as a x-axis, x direction. Okay, so at x equal to 0, T equal to T1, so temperature is equal to T1. At x equal to B, T equal to T2. So at x equal to 0, T equal to T1. At x equal to B, T equal to T2. So we are going to apply these boundary conditions to equation 2 and equation 3. Let me revise. Let me write equation 2 and equation 3 again. So dt by dx equal to C1, it was equation 2, and t equal to C1x plus C2, it was equation number 3. So applying boundary condition 1 and 2 to equation 2 and 3, we have so what do we have? At x equal to 0, t equal to t1. So equation 3 will become t1 equal to 0 plus c2. Therefore c2 equal to t1. Therefore c2 equal to t1. Now let us see how to find the value of C1. Now how we are going to get the value of C1? So at x equal to B, t equal to t2. In same equation, from equation 3. So from equation 3, what do you have? T2 equal to C1, we don't know, x we know it is B, plus C2 we know it is T1. Therefore C1, solve for C1. C1 will be equal to T2 minus T1 divided by B. T2 minus T1 divided by B. So this will become your C1. Okay? Therefore, from equation number 2, dt by dx will be equal to C1. That one will be equal to T2 minus T1 upon B. So this is your temperature profile. Now we are going to apply the Fourier law. Okay? So this is your not temperature profile, it is a slope. dt by dx equal to C1 equal to T2 minus T1 divided by B. While the temperature profile, it has been given by putting value of C1 and C2 in equation 3, we get temperature profile. So what was the equation? T1 equal to C1x plus C2. So C1 we have identified it as T2 minus T1 T2 minus T1 divided by B into x plus C2. Here the C2 is nothing but your T1. So this represents your temperature profile. Okay, so T1 will get cancelled. T1 will get cancelled. What it is going to reduce? Therefore x equal to B upon T1 minus T2. So at this length you are going to have the temperature. Okay. Further, applying Fourier's law, what do we have? Q equal to minus Ka dt by dx. Okay. And recently we have found out the value of dt by dx as T2 minus T1, where dt by dx was found T2 minus T1 upon B. ठीक है. So putting this equation, Q equal to minus KA T2 minus T1 upon B. ठीक है. So this negative sign will go inside. Q equal to KA T1 minus T2 upon B. So this will be the final heat transfer rate in a case of a slab. So this has been derived with the help of heat conduction equation in a Cartesian coordinate. ठीक है.